Good morning. This is Hope Reactor. Now, let's begin today's news.
Scientists found a way to restore the strength of degraded plastic. A plastic molecule breaks apart. Normally that means the material becomes weaker, more brittle and harder to reuse. But researchers are exploring a different idea. Instead of simply melting old plastic and turning it into a lower quality product, they are reconnecting the broken molecular chains inside it. In other words, they are not just recycling plastic, they are repairing it. And by measuring the molecular weight of the repaired plastic, it may also be possible to predict how much strength it will recover. What we don't know can become hope. This is Hope Reactor. Plastic is everywhere. It is inside cars, smartphones, home appliances, electrical connectors, machines, and countless products we use every day. Some plastics are simple packaging materials. Others must resist heat, impact, electricity, and repeated use. But even strong plastic does not last forever. Over time, heat and moisture can damage its internal structure. The surface may still look normal, but the molecular structure is changing. Many plastics are made of very long molecules called polymers. Imagine thousands of long threads tangled together. Those chains help the material hold its shape and resist force. But when plastic is exposed to heat, moisture, or repeated processing, some of the chains can break. Long molecular chains become shorter. As that happens, the material may lose strength and become easier to crack or break. This creates a major problem for recycling. We can collect used plastic, melt it, and shape it into a new product. But a new shape does not guarantee the original performance. The plastic may look reusable even after its internal structure has weakened. It is then often used in products that require less strength, a process called downcycling. So researchers are asking a different question. What if we could reconnect the broken chains? One possible answer is a material called a chain extender. A chain extender reacts with the ends of broken polymer chains and helps join them together. Imagine a long rope cut into several short pieces. Instead of throwing them away, you add connectors between the ends. The rope becomes longer again. At the molecular level, something similar can happen inside degraded plastic. The research focused on PBT, or polybutylene terephthalate. PBT is an engineering plastic used in automotive parts, electrical components, connectors, and electronic devices. It resists heat, insulates electricity, and can be processed into precise shapes. But repeated use or high-temperature processing can degrade it. Its molecular chains become shorter, and its mechanical performance declines. Researchers added a chain extender to degraded PBT. The goal was to reconnect the shortened chains and increase their molecular weight. As the chains became longer again, the material's strength also recovered. This does not mean every damaged plastic can instantly become identical to brand new material. The result depends on the type of damage, the amount of chain extender, processing temperature, contamination, and the condition of the original plastic. A weakened material does not always have to be treated as worthless. If its internal structure can be repaired, part of its lost performance may be restored. And this research goes one step further. The scientists also examined the relationship between molecular weight and mechanical strength. Molecular weight can be used as an indicator of how large and long the polymer chains are. When chains break, molecular weight decreases. When a chain extender reconnects them, it increases. By linking this change to strength, researchers may be able to estimate how strong the recycled material will become before it is used in a final product. Industrial recycling cannot depend only on trial and error. Manufacturers need to know how much chain extender to add and whether the repaired plastic will meet the required standard. If strength can be predicted from molecular data, recycling becomes easier to design. A manufacturer could begin with the strength required for a component, then work backward to determine the necessary molecular weight and processing conditions. That could reduce wasted additives, failed products, testing time, and cost, while opening more demanding uses for recycled engineering plastics. Today, many recycled plastics move down the value chain. A strong industrial material may return as a lower performance product, but if its molecular chains can be repaired and its strength reliably predicted, high-performance plastic may return to high-performance uses. Parts from cars or appliances could become valuable materials again, instead of waste after one life cycle. This could reduce the demand for newly produced plastic and lower the amount sent to disposal. However, there are still important limits. Plastic waste is not uniform. Different polymers require different chemistry. Damage caused by heat may not be the same as damage caused by ultraviolet light, chemicals, or contamination. Mixed plastics are also difficult to treat because they may react differently during processing. Collection, sorting, additives, quality control, and safety standards must also be considered. So this technology is not a universal cure for all plastic waste, but it represents a meaningful shift in thinking. For decades, recycling has often meant melting, reshaping, and accepting lower performance. This approach asks whether we can preserve value by repairing the material itself. In the future, a recycling plant might measure the molecular condition of used plastic, calculate the exact treatment it needs, and restore it with a customized formula. Artificial intelligence and predictive models could help determine how much chain extender to use and what processing conditions would produce the desired strength. A factory like that would not simply recycle plastic. It would act more like a hospital for materials. Some plastic waste may not be truly useless. It may simply contain molecular chains that have lost their connections. Reconnect those chains, and the material may gain another life. A small repair at the molecular level could support a much larger change, from a society that throws materials away to one that keeps their value in circulation. Did you know that degraded plastic could potentially be repaired from the inside? And if we could restore one plastic product instead of replacing it, what would you want to save? Tell us in the comments. Here at Hope Reactor, we explore science, technology, and ideas that can turn today's problems into tomorrow's possibilities. If you enjoyed this video, please like, subscribe, and join us for the next story. What we don't know can become hope. This is Hope Reactor.